Yeah, this is Lavanya, KREC, HMS Department, Physics. So today my topic is semiconductors in that, some Hall effect. So we'll be talking about Hall effect. So when a current carrying a material or a semiconductor is placed in a transverse magnetic field, when a potential difference is developed across a semiconductor, which is mutually perpendicular to both electric and magnetic field. This phenomena is known as a Hall effect. And we'll be talking today about the Hall voltage also. So the voltage produced in this phenomena is known as Hall voltage. So this is the circuit diagram. So magnetic field and electric field. So this is a conductor we are taking. It is connected to the battery. So this is a magnetic field and electric field. So this is the width of the material. Okay, length of the material. All positive charges are onto the one end and negative charges onto the other end. And potential difference is developed over there. So here, electric field and magnetic field both are perpendicular to each other. So which is maintained, and the voltage where it is developed is Hall voltage. So this is a circuit diagram. If you are observing, all the negatives will be onto the one side and the positives will be onto the other side. So from Lorentz force, FL is equals to small e into capital E. So capital E is the applied electric field and small e is the charge of the electron. And when you apply the magnetic field on the charge, so FB is equals to BE dV. So where dV is the drift velocity, V is the magnetic field. So from 1 and 2, both the forces, Lorentz force and magnetic force, 1 and 2 combined together, you will be getting the equation 3, EH is equals to VD. EH is equals to VDV. So this is how you are replacing equation, equating equilibrium position takes place over here. So as both are in perpendicular to each other, magnetic field and electric field. So this is how it is taking place. So when you simplify this one, you will be getting in terms of electric field and magnetic field, EH is equals to V dV. EH is equals to VD. VD is the drift velocity. So from equation 3, we'll be getting H is equals to VH by D. So this gives the equation 4. So VH is a Hall voltage and D is the thickness of the sample. So small d is the thickness of the material, whatever the material you are taking place. So D is the thickness of the sample. So from the above equation, now substitute equation 4 in the equation 3. So what is equation 3? EH is equals to VdV. So when you substitute over there, you will be getting in the place of EH, you write substitute equation 4 in equation 3. VH by D is equals to VD. Then by simplifying that, we will be getting equation 5. VH is equals to VD into D, small d. So VD is the drift velocity over there. D is the thickness of the material, whatever you are taking. So due to the Hall field, there will be a development of a current density. Current density is denoted by J. So J is equals to NEVD. NEVD. VD is equals to J by NE. So VD, drift velocity, we got it. That is equation 6. Equation 6 is the drift velocity. So after getting drift velocity, whatever the drift velocity you are getting, substitute in equation 5. Substitute equation 6 in equation 5. Then by simplifying that, we'll be getting equation 7. That is, as you are seeing, VH is equals to Bj by NED. But we know that the current density is denoted by J. In terms of the J, in terms of current, J is equals to I by A. A can be written as dW. So D is the thickness of the sample, W is the width of the sample. Substitute 6 and 7 in equation 5. Substitute 6 and 7 in equation 5. Then we are going to get equation 9. By simplifying this one, so VH is equals to B by dW into 1 by NE into D. D is the thickness of the material once again. So this equation represents the Hall voltage. VH is the Hall voltage. So how to get the Hall coefficient now? We got Hall voltage by simplifying all these derivations. So this is a derivation by taking Lorentz force, magnetic force, okay, electric field and all those drift velocity, thickness and all. We got the Hall voltage. Now we'll see Hall coefficient. How we are going to get the Hall coefficient? It can be defined as it is a ratio of the electric field across a semiconductor to the current density per unit volume per unit magnetic field. So then RH is equals to EH by JB. EH by JB. So EH is denoted by VH by D. VH by D. VH by D into 1 by JB. So this is from equation 4 we got Hall coefficient. So we need to simplify to reduce this one. We need to simplify more and more so that substitute equation 4 in again 7. Then we'll be getting RH is equals to Bj by dNe. So this again simplify it as RH is equals to 1 by Ne. So this is a Hall coefficient. RH is known as Hall coefficients. Now we'll see what are the applications of the Hall effect. What are the applications of Hall effect? Hall effect is very useful in the phenomena of semiconductors. So many types of semiconductors it will be useful. In N-type semiconductors, in P-type semiconductors. So in a negative and a positive cases. So RH is negative in N-type semiconductors and positive in P-type semiconductors. So for calculation of carrier concentration also, this RH is useful. RH is means Hall coefficient. It is useful. Mobility also. In mobility also it is useful. Mobility means the expression for the number of electrons or the number of holes. Mu. So for measuring magnetic flux density also, RH is very useful. And in the formation of PN junction also, PN junction formation also is very useful. So in the PN junction formation, so how the formation of PN junction takes place? A PN junction is formed by joining P-type and N-type semiconductors. Gather is very close in contact. The term junction refers to the boundary interface where two regions of the semiconductors meet. So this is how when you join the P-type and N-type regions, So you will be getting a boundary interface where two regions will meet together. So this is how this diagram is showing how they are interacting. Next, in N type, it's a donor ion represented as the plus sign because it's an impurity atom, donates the electron. It because the positive ion and the p-type acceptor ions is indicated by the minus sign because after the atom accept the electron, it becomes a negative ion. After accepting, then the electron will become it will become a negative ion. So this is how a positive and a negative charges. So in this p-type and n-type region, when you combine, a junction is forming over there, and that junction is known as a depletion region. Also, you can call it as, so the space charge region. You can call it as a space charge region also. So there is a large concentration of holes in the p-type material and large concentration of electrons in the n-type material. So because there is a density uh, gradient across the junction, so the holes will initially diffuse to the right across the junction and the electrons to the left. The flow of holes and holes from P region result to the negative charge acceptor ion, and the holes of electrons from negative region leaves positive charge donor ion. And this is how when you combine both p-type and n-type, you will be getting the p-n junction formation is taking place. Okay, this is how we'll end this one, end the session.